Picture a brutal game of tug-of-war. Two perfectly matched teams pulling with everything they have, digging their heels into the mud. But look right at the center of the rope. It is perfectly still. That hovering rope is actually showing us a basic rule of physics. Every movement you see, and every time something stops, is caused by invisible pushes and pulls. We call these pushes and pulls forces. To keep track of these pushes and pulls, scientists use a scoring system. Instead of points, they measure the strength of a force in something called newtons. This diagram shows exactly how we measure that score using a tool called a Newton meter. You see one measuring the pull needed to drag a shoe and another measuring the downward pull on a single apple, which is about 1 Newton. When pushes and pulls cancel each other out, we get a balanced force. Think of a kid sitting on a park bench. Gravity is constantly pulling them down toward the earth, but the bench is pushing back up with exactly the same Newton score. Because those two forces are perfectly matched, the kid doesn't move. So when an object is completely still, it doesn't mean there is nothing acting on it. It just means the tug-of-war is currently tied. Now let's put wheels on that park bench and have a friend walk up and give it a hard shove. Suddenly, we have a push in one direction that has no match. We have an unbalanced force. This diagram shows what happens when forces are uneven. One person pushes a box right with 20 newtons, another pulls right with 15. With no equal force fighting back from the left, the box speeds up and moves right. But think about our kid on the wheeled bench. After that single shove, why do they eventually slow down and stop? They stop because there is an invisible opponent pulling backward, called friction. Even smooth surfaces are rough up close. If you zoom in on a wheel and a road, you see tiny jagged peaks and valleys. As the wheel rolls, these tiny ridges lock into each other, catching and resisting the movement. If you roll that same wheel through a puddle of water, the liquid fills in those microscopic gaps, creating a smooth layer. This stops the rough edges from catching, which reduces friction and makes everything slip. Look at this illustration of a swimmer to see how friction works in fluids. When moving through water, you must physically push the molecules out of your way. The water fights back, opposing your motion, creating water resistance. Every time a moving object slows down on Earth, friction is the culprit pulling it to a halt. To really test how this works, we need to leave Earth entirely and head into outer space, where gravity behaves very differently. First, we need to clear up a common mix-up by looking at mass. Mass is just the raw amount of physical stuff an object is made of. We measure it in kilograms, and your mass never changes, no matter what planet you are standing on. Weight, on the other hand, is completely different. Weight is a force. It is the specific Newton score measuring exactly how hard a planet's gravity is pulling down on your mass. This data table shows the difference clearly. Look at the 1 kilogram object. Across Mars, Mercury, and Venus, its mass stays exactly at 1. But the force of gravity, its weight, measured in newtons, changes drastically depending on how hard each specific planet pulls on it. So, when you step on a bathroom scale, it tells you nothing about how much of you exists. It only measures how hard the Earth is currently pulling you toward the ground. Back down on Earth, forces also change the shape of things. Think about grabbing a thick rubber fitness band and pulling the ends apart. When you apply that pulling force, the rubber band doesn't sit passively. Because of a rule called action and reaction, the band exerts the exact same amount of force, pulling right back against your hands. These stretchy materials follow a highly predictable mathematical rule known as Hooke's law. The rule is simple. If you double the strength of your pulling force, the stretch of the band, its extension, will exactly double. This graph displays Hooke's law in action. By plotting the pulling force on the bottom against the extension on the side, we get a perfectly straight diagonal line. That straight line proves the stretch is directly proportional to the force applied. Even objects without muscles, like rubber bands and metal springs, fight back using strict mathematical rules. They play the exact same game of tug-of-war. Let's put all these pieces together. Imagine a soccer player sprinting toward a ball and kicking it with absolute maximum effort. At impact, unseen pushes and pulls light up as arrows. The massive forward kick is an unbalanced force, overwhelming the rest to shoot the ball downfield. But smaller arrows fight back. The ball pushes back with a reaction force, and air creates friction. This exact same network of invisible arrows surrounds you right now, whether you are driving a car, swimming in a pool, typing on a keyboard, or just standing perfectly still. Take a look around the room you are in. Find an object that isn't moving, and picture the perfectly balanced arrows keeping it there. You are always an active player in the universe's ultimate game of tug of war.